thank you for this nice introduction. Zagorac is my wife. She is the first author, and I'm the leader of the group, so I will present the results. And thank you, the organizers, for letting me, Professor Gal, for introduction. And today, actually, I will talk about mechanical properties of solid solution of hafnium and tantalum carbide. And this is done on ab initio level, it means atomistically. So a bit different from what you have heard or you will hear in the future. But I come from a bit different field, and I'm professor at the University of Belgrade, and I have my own group laboratory for theoretical investigation of materials, and we have our Center of Excellence, and actually we are located in Institute of Nuclear Sciences. So just for introduction, the introduction is that you have hafnium carbide and you have tantalum carbide as a refractory material. They have very high melting point, about 3,900 degrees Celsius. They have very nice mechanical thermal effective properties. You have very high Vickers hardness exceeding 20 gigapascals, and it can be used as cutting tools. You can see actually it can be used for hypersonic materials, for nuclear plants, cutting tools, etc., etc., etc. So, what happens with pure tantalum carbide and hafnium carbide? They actually crystallize at atomic level as this nice cubic structure, which is called the Roxel structure, and it appears in this Fn-3m space group, which is 225. And there you have actually tantalum in the middle, and it's surrounded by 6 carbon atoms around, and it's the same with hafnium. So hafnium can be inside, and it's surrounded by 6 carbon atoms. And when we calculate this on this DFT level, this atomistic level, then you have these results, which my pointer works. Okay, I'll show you with the pointer. So this is our results. There is this method which is called LDA and GGA, and these are our results here. And when you compare it with experiment, you see actually that we have very good agreement, and there is a lot of experiments also in previous theory done, also with GGA and LDA and other theoretical methods on atomistic scale, and we have very good agreement with that. And actually, there's some reference data where actually published it. We recently published this on pure tantalum carbide and pure hafnium carbide. But here, actually, I want to show you something. What happens when you mix hafnium and tantalum carbide? When you make mixed alloys. So, yeah, this is actually the result. What happens if you calculate pure hafnium carbide? So the lowest total energy when you calculate this at atomic level, this is the black line. This is the Roxel structure. This is the cubic one, the nice ordered structure. But you see, actually, you can calculate a lot of different structures at higher energy, which can appear at high temperatures, at high pressures, etc. And you can have like thallium iodide type, different kind of prototypes, nickel arsenide rock, etc., etc. And actually, that's we already published. And actually, if you calculate thallium carbide as a pure also, again, you see that the total energy level, the energy versus volume, that's something which theoreticians usually calculate at atomistic level. They calculate this energy versus volume curves. And then you see actually, again, the lowest energy minimum is this Roxel structure, the cubic one, 6-fold coordinated. But you can again see a lot of different structures depending on the pressure and temperature. Okay, but in this study, I want to show you what happens when you mix hafnium and tantalum carbide, and these are the mixtures. So if you have 12.5% of hafnium, then you have 87.5% of tantalum carbide, and then you have 25% of hafnium, and so on, so on, so up to 100% of hafnium or 100% of tantalum. And we investigated mechanical elastic properties, which includes bulk modulus, shear Young moduli, elastic constants, and Vickers hardness. And this was done in combination of atomistic DFT methods on one side. On the other side, we invented a new Coven method. I will say just a few words. There is the references there if you're interested in this. So from DFT methods, we actually used the ab initio calculation. So this was done in crystal 17, crystal 33 code, which is based on linear combination of atomic orbitals. And from DFT methods, in this case, we used LDA and GGA. And as I said, there was a good agreement between experiment and theory. And actually, you can see that for the pure hafnium carbide, which is calculated for the LDA, this is the bulk modulus. It's 261. And experiment is value up to 263. There is also previous theory which is higher, etc., etc. So shear modulus is again the same value as the experiment, Young modulus, and so on. So more data actually you can find in this paper. So similar it is with the pure tantal carbide. There is even more data there. So we have published bulk modulus 361. It goes in experiments. It can be even higher depending if you have nanostructures, if you have different kind of density of the structures, etc. But in principle, we have very good agreement between theory and experiment. It goes for shear modulus, goes for Young modulus. Poisson ratio is basically the same as experiment, and hardness is a bit higher than an experiment, but it's as in previous calculations also found, etc., etc. So this is also for pure tantal carbon, pure Hafnium carbon. Actually, on the right side, you can see also for some different structures at higher temperatures, higher pressures in pure tantalum carbon. But what happens if you mix these two structures? Actually, now I'm showing a paper which we recently published in Crystal Growth and Design. And this is now Coven algorithm which we invented. So even in atomic level, if you have one pure substance like hafnium carbide, and now you put a bit of tantalum or more, or whatever you want to put inside, you distort the structure. You lose symmetry. Something happens, something breaks. And this is the problem. The experimentalists solve this by making partial occupancy on one atom. This is a problem for outer addition, especially on atomic level, because we cannot cut atoms in slice. We put enough atoms and we create a large supercells. So just briefly show you, because I don't have enough time. If somebody's interested, I can explain more deeply how this Coven algorithm works. But in principle, it solves this problem. So in principle, this is short for keep original vectors in new structure and address this problem. So in this case, it was done for lanthan fluoroselenide. Was done experiment in a nice group in University of Stuttgart and Max Planck Institute in Stuttgart. And we did the theory. And once we did the theory with the full relaxation of atoms, then of course you get different results of properties. But once we apply the Coven algorithm and return back the structure to the original state, we actually get exactly the electronic properties in this case as people measure it in Germany. And the same approach we use now for hafnium tantal carbide, but just for mechanical properties. You can use for any properties you like. So this is the result. And the result actually you can see in this big table, the first column is tantal pure tantal carbide. The above is the LDA version, the below is the GGA version. And now you can see actually that by inserting a bit of hafnium, so 87.5% of tantalum, it reduces the bulk modulus to 376. But then if you have 75, so more hafnium in the structure, then it's even less, and up to pure hafnium carbide, which is 261.54. Of course, this is all calculated by Voigt, Royce, and Hill is the approximate. So in principle, this value is here. So confirmed with two different methods, you get the same trend, which increasing tantalum, you have the increase of bulk modulus. And you actually see that the shear modulus is similar. So by having less tantalum in shear modulus, why the pointer does 279, and then it goes down to 193 with the pure hafnium carbide. And same is with the Young modulus. You go down up to 466, and the same with the GGA. So when you calculate Poisson ratio, it's not the same issue. With the Poisson ratio, depending on the tantalum carbide, you can have different kind of variation in Poisson ratio. Weaker hardness also depends on, does not behave on the same trend. We calculate actually the elastic tensor for this different kind of solid solutions. And finally, we calculated the fracture toughness, which fracture toughness reduces with the reducing of tantalum, as in previous case for the different elastic modulus. Also, I'll show you some graphs, and actually you can see that how the weaker hardness is the less is appearing in this trend, while other elastic modulus have this trend of decreasing with decreasing tantalum amount. And on the other side, you can see the elastic constants in all of these different tantalum amounts, and you can see actually that perhaps the biggest influence is the C44 elastic constant. Okay, to conclude, I have calculated all of this. We have calculated all of these half and tantalum carbide solid solutions. We have investigated a different kind of elastic modulus and elastic constants, and this was computed together with DFT methods and new Covenant algorithm. We note that there is the trend, that increase of tantalum and the increase of the elastic properties with in solid solution, and we believe that this study is very important to understand structure-property relationship in half and tantalum solutions. At the end, I would like to thank Professor Zagorac, who is from my group, Professor Schön, who is from Max Planck Institute, collaborating with Professor Milos Djukić from University of Belgrade, Dr. Matej Fonović from University of Rijeka, which we collaborate on this project, Professor Maksimović, Tamara, Škundrić, and Milan Pejić, and also thank you